Hey class, welcome back to Electromagnetics. So this lecture we're going to take a quick minute to look at lines with initial conditions. First we're going to look at the inspirational thought. It's from Philippians 1:3-6. I thank my God every time I remember you. In all my prayers for all of you I always pray with joy because of your partnership in the gospel from the first day until now, being confident of this, that he who began a good work in you will carry it on to completion until the day of Christ Jesus. And so of course the emphasized part there talks about how God started the work and starts the work in us. So that's kind of like the initial condition, but then it has to be worked out until its completion, until the day of Christ Jesus. And so we're kind of parallels what we're talking about today with initial conditions on a transmission line and how we can work through that and through different times and how it can affect our circuits. So again, we're still in part 7. This will be the next to the last lecture in this segment, and again, lines with initial conditions. So up to this point, all the scenarios that we've been looking at have been lines with no initial voltage or current on them. So now we want to examine the effects of a non-zero initial condition for voltage or current on the analysis and performance of a transmission line. So this may be something that's kind of new for you to think about because up in with your network analysis up to now, you've probably dealt with just circuits that, until you close a switch or something, nothing's going on. And that's true many times, but when you get in high performance circuits, especially high speed circuits, there are times where you can have switching transients and things going on that if you don't time it correctly, when you open a switch and then shut it sometime later, there still could be some initial condition on it. So just want to give you these tools, put in your tool bag, and this is a little bit of a prelude to looking at interconnection between logic gates, which is the condition I was just talking about, that this can happen, where this can happen. So to begin this analysis, we want to consider a line that is open circuited at both ends. So there's no source, there's no load, it's just the transmission line. And so we want to consider the situation where there's some initial charge on this line. And so if we look at, we have the line defined here from z equals 0 to z equal L. We do have an impedance and a time period associated with this. And so if we look at the profile of the voltage across this transmission line, that is between the two lines, we'll see that it starts out at 50 volts. We get to the halfway point of the line, and then it starts to descend until we get to the end, z equal L, to where the voltage is 0. In the same manner, if we look at this transmission line, we're going to see that there is a current profile as well. There's no current at either end, but the current is maximized at the center of the transmission line. Now, I know this is kind of hard to visualize since it is an open circuit, but just bear with me as we continue the analysis here. So with this, we can now write expressions for the voltage and the current in terms of transmitted and reflected components, since we've been looking at that up to this point. So remember, to do that, we can say that the total voltage on the line, this is for all z, is equal to some forward transmitted voltage across all z, plus some reflected voltage across all z. Same thing for the current. The total current on the line is a result of some transmitted current plus some reflected current. We can replace in the second equation the transmitted and reflected current with V, the voltage over the impedance. So when we do that, this changes our second equation then to be in terms of the transmitted and reflected voltage again, this time equal to the current times the impedance, which is just Ohm's law. So bringing those equations forward, this is two equations, two unknowns, because we know the voltage, we know the impedance, we know the current profile, we don't know these transmitted and reflected waves. So we can solve for those, and when we do, we see that the equation for the transmitted voltage is 1/2 of the voltage on the line plus the impedance times the current on the line, and this is for all z. So at any point z, you can evaluate all these terms. Same thing for the reflected voltage. That again is 1/2 of the voltage again minus this current times the impedance. So what does this look like? We can look at this graphically now. So this was our original voltage, right? So if we think about those equations, this voltage here at Z equals 0 says that the transmitted wave, which would be the second line of graphs here, is equal to 1/2 the voltage, so this is down 1/2, plus the current times the impedance. Well, we know that the current at that point is 0, so it doesn't matter what the impedance is, so we're left with just half of that voltage. Same thing for the other end. We see it at Z equal L. 1/2 of 0 is 0, and then plus the current times impedance here is 0, so we're still at 0. And so we can do this for every point Z on the line. You can see that the transmitted voltage is maximized in the middle. Of course, this is where the voltage is equal to 50, and we do have the current times the impedance there. Likewise, the reflected wave is again 1/2 of the voltage minus the current times the impedance, and so we can do that for every Z here. And so what you'll find then is this total voltage wave here is these two added together. So if you were to take this slice here, it kind of fills in this slice here, which makes this constant across there. So the bottom graph plus the middle graph equals the top graph. And the same thing goes for the current. We can add these together. If you were to take this slice here, except in this case, it's below the z-axis, so it subtracts. So it actually takes this sliver out here, and that's what gives us the overall profile at the top. So we can deduce what the conditions are then after 5 microseconds. And here what happens is that all the curves just shift. So before we had, I believe A was here. So if we're already at the end, so we have to go back. So 1, 2, 3, 4, 5, that would put us in the middle. So here you see the A point down in the middle, and so on and so forth. Each of those points you can shift, and so as it shifts, the reflected and the transmitted voltages both shift, and we still add these together though. And so the overall profile after 5 microseconds would be this waveform plus this waveform after it's been shifted 5 times. And you can see here is the resultant. We still, at Z equals 0, we'd have no voltage, and we'd have the maximum ZL. It's the same thing with the current. You can see here is the transmitted current. This is the reflected current. So again, this is below the z-axis, so it subtracts, and so we're left with this profile for the current. Again, this is after t equals 5 microseconds. We can shift it as many times as you want. It's a cyclical shift, and just however many time period you have is how many times you shift it. So that being the case, we could take the initial conditions then and deduce the voltage across a resistor if it were placed at the end point Z equal L at t equals 0 seconds. And what happens then is the waveform plays out. So we had the point A was at that load point, so that the voltage there initially would be 0, and then the B point slides to the right, so then we have at half a microsecond 50 volts, then C slides over, so it would be 25 volts, and then finally we get D, which was 0 again. So sometimes if you have some initial charge or initial condition on your transmission line and you shut the switch, you might see some transients like this. And this is common, especially if you have capacitance on your line. So remember, capacitance can store charge or store electricity. And so you most definitely could see something like this if you have a highly capacitive line.